Hello, Mr. Wilkinson here. This is going to be a chemistry paper 1 higher combined breakdown. What I'm going to do in this is I'm just going to break down each question into the thought process behind how to get to the answer or what I'm thinking when I'm seeing these questions, and hopefully it'll simplify the questions for you when you do your GCSE exams, so you don't need to overthink it. You can just highlight key phrases or key words that give you a clue as to what sort of topics link into this question and what the question is going to be asked of you. So here we go. So for this question, it says this question is about salts. We're reacting green copper carbonate and sulfuric acid to produce blue copper sulfate crystals. So green copper carbonate, sulfuric acid, product is blue copper sulfate crystal. It already tells you what the colours of the things are. Sometimes you will be expected to remember that. The first thing I'm thinking is it's talking about a metal carbonate reacting with an acid. Metal carbonates are alkali, metal oxides are as well. So if you've got an acid and an alkali, you've actually got a neutralisation reaction, and this will become relevant in one of the later questions. I'm also spotting the fact that it says carbonate. When you have a metal carbonate, one of the products that you end up with is CO2 gas being produced. So we'll come back to that. It says excess copper carbonate is added, which means we're adding extra copper carbonate to make sure all of the sulfuric acid is reacted, and we're giving 3 observations of what you would make. All observation means is you just say what you see. So there are quite a few points that you could put for this, but you're just saying what you would see before the reaction, during, after. There's quite a few things you could say. So the first thing you could describe, very simple, is what does green copper carbonate look like? Well, it's a green powder. What happens during the reaction? You put it in. If we're getting CO2 gas being produced, what you would see is fizzing or gas being produced. If you leave it in there long enough, eventually all of this is an extra mark, so all of the copper carbonate, so the green powder, disappears because it's all reacted, and then we end up with a blue solution at the end. You could also mention, what does sulfuric acid look like? Well, sulfuric acid is a colourless solution, has no colour. We could say at the end it stops fizzing. So the reaction's finished, the fizzing has ended, all of the copper carbonate is gone, and that's pretty much it. I mean, you don't need all of those. All you need is 3 of those points to get all 3 marks. You don't need all of those. They're just all of the possible things that you could have said. You're just saying what you see before it, what you see during, what you see after, and that's it. So for this next question, there's 3 on this bit. So it says, how can the excess copper carbonate be removed? So you're thinking straight away you've got excess copper carbonate, which means too much, means it's unreacted, and it says removed. You're thinking separating techniques, all of the separating techniques that we've talked about, right? So there's a list. What technique do you use to get rid of? Well, excess copper carbonate is an insoluble solid, which means it doesn't dissolve. What technique do you use to get rid of an insoluble solid from a solution? That technique is called filtration. Easy enough. Next one, the pH of the solution changes during the reaction. What is the pH of the solution at the end? First thing is talking about acid alkali, isn't it? Remember the pH scale, acid over to alkali, and your scale was numbers 1 to 14. So what number on that scale is it? Now, if you remember back to the previous question, I already told you that it was a neutralization reaction where we've got an alkali reacting with an acid, neutralizing each other. What number is neutral? What number is smack bang in the middle? It's 7. And then the last one, copper carbonate and sulfuric acid react to produce. We already talked about this. Yeah, alkali, acid, neutralization. Next one. So this one, it says ammonium nitrate is a salt. The graph shows the maximum mass of ammonium nitrate that will dissolve in 100 centimeters cubed of water at different temperatures. So one thing you may be aware of, your teacher may have told you, or you may just know this off the top of your head, if you heat up a liquid the salt, the amount of salt that you can dissolve in it will increase. So you can try that at home. You can put a bit of salt in water and then make it warmer. You'll be able to dissolve more in it. Something to do. Along the bottom it says temperature. Along the side is the maximum mass of ammonium nitrate that will dissolve in the water at 100 centimeters cubed of water at whatever temperature it is. So it says they add ammonium nitrate to it at 80 degrees until no more dissolves. So this would be the maximum mass that dissolves. And then they cool the 100 centimeters cubed down from 80 degrees down to 20 degrees to produce crystals of ammonium nitrate. So you've got to determine what the mass of ammonium nitrate crystallizes out when they cool it from 80 to 20. So the first thing you need to figure out to do that is figure out how much ammonium nitrate will dissolve at 80 degrees Celsius. And that's where the graph comes in. So you can use your ruler for this. You can draw a line. I'm going to struggle to draw a perfectly straight line, but I can see it. So you go up to the line at 80 degrees, straightest line you've ever seen, and then you go across. So what it is it's actually 1.5 squares above from 80. So the first thing we need to figure out is how much is each little jump worth. The way we do that, if we look at 0, simplest way to do it, there are 5 little jumps from 0 to 10. So that means each little jump is worth 2. So if we're at 80 and we do 1.5 little jumps, that's going to be 3, right? So we write down first at 80 degrees Celsius, 83 grams dissolved. Right, one thing you can do on this one is there is a bit of a range for it. So if you misread the graph, you can have a range of somewhere between 82 to 84, but the correct number is 83. And then we do the same for at 20 degrees. So how much dissolved at 20 degrees? Go up to the line, and then we go across. So that's one little jump up from 30. So that's going to be 32 grams. So at 20 degrees Celsius, 32 grams dissolved. Now you can have a range for that one. You are allowed either 32 or 33. And then what we need to do is we work out how much crystallizes out when we cool it down, because not all of this 32 grams, not all of this 83 grams of the salt will be able to dissolve at 20 degrees Celsius. Only 32 will. So we need to figure out how much is left over that's going to crystallize. So to do that, we just calculate the difference. So 83 take away 32 gives you 51 grams. For this question, if you mess up these numbers and you do 82 and then you do 33 for the other one, as long as you did the maths correctly at the end, you can still get the third mark. So the maths has to be correct based on the numbers that you chose on your graph, but it has to be between these ranges of numbers. Next question. So this next question is about electrolysis. So the first thing I'm thinking when I see the word electrolysis is it's talking about the separating of something, splitting it up into its ions, positive and negative go into each electrode. It talks about using potassium sulfate solution, so it gives you a hint as to what the ions would be that come out of that. And then it mentions inert electrodes, something to think about. Inert just means they are unreactive, so they are not a factor in this. It means that they'll last a long time. So then it says potassium sulfate contains K plus and SO4 2- ions. The only thing I'm really thinking about this is the charges on the ions. What is the formula for the potassium sulfate? If it's a formula, the overall charge of the compound would be 0. So they need to cancel out, because otherwise, as soon as it's got a charge, that means it would be an ion. So those two charges, the charges of the potassiums and the charges of the sulfate ions, must cancel out. So we're just doing some simple maths. So we're figuring out how many of those potassium, if it's just a plus, that's the same as it being a +1. So how many potassium +1s do I need to cancel out sulfate 2-? How many +1s do I need to cancel out 2-? I need 2 potassiums. So I need 2 times potassium ions. And we just figure out which ones of these cancels out so that it's at 0 charge. We can test it. You'll figure it out, the answer, pretty quick, but I'll just do the first one to show you the method. So in this one, we've got 1 potassium. which would be overall +1 charge. And then we've got one sulfate group, sulfate ion, which would be 2-. That would cancel out to -1 overall charge. It's not that one, because if it's got a charge, it would be an ion. So let's try the next one. We've got 2 potassiums. That would be 2+. And then we've got sulfate ion, 2- overall. That cancels out to 0. So the answer, I mean, that's going to be the one. That's the one that cancels out the charges, but you can check it if you want to go through the method. The next one down, we have 1 potassium, so that's going to be a +1 overall charge, and then we have 2 sulfate ions, which would overall be 4- or -4. That would cancel out to -3, so it can't be that one. And then the last one, 2 potassiums, +2 overall charge, and then 2 sulfate ions, which is -4 overall charge. That would cancel out to -2. So it's got to be the second one. This next question is still about the same electrolysis setup, so you're still using the same diagram. So it says figure 2, and bold writing, need to be using figure 2 to help us with this question in particular. Shows you the setup, shows you the measuring cylinders upside down, one with oxygen appearing in it as a gas and one with hydrogen. And it says, what are the volumes of gases collected in the electrolysis experiment? So the first thing we need to think about with this is you're talking about gas. So what people are going to end up doing with this most of the time is you're reading the volume of gas that's appearing in each measuring cylinder for oxygen and for hydrogen. And what people end up doing is they read it from the bottom and they think, oh yeah, I read a measuring cylinder. Normally when you fill it up from the tap, it goes up like a liquid does. But with this one, you have to think it's a gas being produced. You can see the bubbles forming. The bubbles would go up, rise up through the measuring cylinder, and then the measuring cylinder would actually fill from the top. So it's filling from the top down, and then it's pushing the solution out of the way. So you're looking at the measuring cylinder kind of upside down. It says the measuring cylinder is 50 measuring 50 centimeters cubed of volume. So the very bottom line is 50. And we need to figure out what these lines represent. So how many big jumps is it to get to 50? 1, 2, 3, 4, 5. That means each one on one of these jumps is 10 centimeters cubed. So obviously half of that is 5. So let's look at the hydrogen one. So we read it. I'll change the color for this one so you can see what I'm doing. So hydrogen, we're reading it from the top down. So we've got 10, 20, 30. So 30 centimeters cubed for hydrogen, and then for oxygen we've got 10, and then halfway to the next, so 15 centimeters cubed. It's pretty easy. It's just general measuring, using your ability to read measuring apparatus, but just understanding with this one, because you're producing gas and it's upside down, you've got to read it from the top. If you need to, turn your paper upside down and look at it that way. If you find it difficult to do it upside down, just turn your paper upside down. Makes it easy for you. So for this question, it says the student made the following hypothesis. It's like a prediction. The volumes of gases collected in this electrolysis experiment are the same ratio as hydrogen atoms to oxygen atoms in a water molecule. The first thing I'm thinking is ratio. What's a ratio? Ratios are the things that you've done in maths before, is things like 1 to 1, 2 to 1, 3 to 1, etc. And then you've got the key bit for this is it mentions a water molecule. I'm thinking, what's a water molecule? Well, a water molecule is H2O. That just means 2 hydrogens and 1 oxygen. And it says, explain how the volume of gas is collected in the experiment. Figure 2, so the diagram earlier, supports the student's hypothesis. So use the answer that you did for question 0.02.2. So this is the volume of gases question that we did before. So if you remember correctly, I did volume of hydrogen was 30 centimeters cubed, and then the volume of oxygen was 15 centimeters cubed. So now if we have a look at, let's figure out what is the ratio of hydrogen to oxygen atoms in a water molecule. Well, it's 2 hydrogens to 1 oxygen, so the ratio is 2 to 1. And then the same, if we look at our volume of gases, if we put it as a ratio, 30 to 15, so 30 centimeters cubed of hydrogen to 15 of oxygen. If you simplify that down, that actually simplifies to 2 to 1. So you put ratio of hydrogen to oxygen is 2 to 1. You could even specify for volume of gases. And then, so that's your first mark. Second mark, you just say for, so that is the same as the ratio in a water molecule. Now for this one, you can escape making a mistake for this one, because if you messed up the measurements of volume earlier, but you highlight that the ratio of water in hydrogen to oxygen in water is 2 to 1, but yours doesn't match that. So for example, let's say you did hydrogen was 31 and oxygen was, I don't know, 14. You could say the ratio is not 2 to 1, so it is different to the ratio in a water molecule. So you can get away with getting those marks even if you did not measure the volume earlier on. You just say the ratio is not 2 to 1, so it's different to water molecule. That's another answer that you could have done, but this is the correct answer. Next question. So this experiment was repeated 4 times. The volumes of oxygen collected in the 4 experiments are these following numbers. The mean volume that collected was 9 centimeters cubed. So mean, straight away I'm thinking what they've done there is they've done this plus this plus this, added them all together, divided by however many there are, which is 4. Then it says measure the uncertainty. The measure of uncertainty is the range of a set of measurements around the mean. So it's the range is the difference of how far away from the mean that it is. What is the measurement of uncertainty in these 4 experiments? So you find the mean. This is the mean, right? And then if we go up, so we're trying to find out how far is the range above and below from the mean for these measurements that we've got, right? The highest one we've got is 11, and the range of that is 2. That goes up by 2. And then if we go the other way, the lowest one is 6, and that goes down by 3. So you're picking the measurement of uncertainty is plus or minus, because the biggest one is actually 3. So it's going to be 9 plus or minus 3. So for this one, we've got 0.86 grams of potassium sulfate dissolved in a volume of water, 25 centimeters cubed. And it says calculate the mass of the salt needed to make 1 decimeter cubed of solution. So the first thing you need to highlight with this one, I'm thinking, is these 2 units are different. So the first thing you need to think about is how do I convert that one of them into the other unit to make sure they're both the same before you can do anything further than that. So what you need to do is I would just turn centimeters cubed into decimeters cubed. Now, the thing that stumps everybody for this one is because it is cubed. So a decimeter is just 10 centimeters, but because we're talking about volume, it's going to be cubed that. So it's going to be 10 times 10 times 10, which is 1,000. So to convert 25 centimeters cubed into decimeters cubed, you need to divide by 1,000, which will give you 0.025 decimeters cubed. So what we've just worked out there is we've worked out that this much 0.86 grams of potassium sulfate is enough to make 0.025 decimeters cubed. So what you need to do then is figure out, well, what do I need to multiply this by to make it up to 1 decimeters cubed? So what you do is you simply do 1 decimeter divided by that number that we just worked out. How many times into 1 will this number go? So 0.025, 1 divided by 0.025 gives us 40. So that means if we want to make the solution up to 1 decimeter cubed, we're going to need 40 times more
potassium sulfate. So all we need to do is do 40 times 0.86 gives us 34.4 grams. So for this one, it says plan an investigation to find the order of reactivity of the three metals. You should use the temperature change when each metal is reacted with the hydrochloric acid. Now for this one, it's talking about a method, so the first thing I would be thinking about for this is the variables. What are the variables in this? Because whenever we do science, things are changing all the time. We want an independent, so something we change, a measuring thing, so dependent variable, and then we want to control everything else, because otherwise our results mean nothing. So first thing I've highlighted is this, the three different metals is our independent variable. That is the thing we are changing. And then the order of reactivity is our dependent variable. And then there are going to be some controls in there, but we'll get to that later. So the first thing we need to think about with this is, what would a logical step be? Almost imagine yourself doing it when you're writing this out. Does it make sense if someone was to read this to actually follow this method? Because that's where the marks are going to come from. That's where you're going to get your 5 and 6 marks, is if someone follows this, does it actually make sense? Is it in a logical order? So the first thing I would do is, you're reacting with a metal and acid, right? You talk them through one of them. So measure a volume of acid, right? And pour it into a cup. I would even use polystyrene cup. Why? Because we're talking about temperature change. Polystyrene is an insulator, stop the temperature from changing too much, lose it to the surroundings, so we get a more accurate result. And what we would do is we need to work out the temperature change. How do we do that? We need to get the temperature at the start and the temperature at the end. So once we put the acid into the cup, we measure the starting temperature. Okay, then what we do is, when we want to get the reaction to start, we place a piece of metal in the cup. And then how do you stop the heat escaping even further? Put a lid on it. Right? So you just put the piece of metal in, let the reaction go, put the lid on to stop it from losing any excess heat to the surroundings. And then what do we need to do? How do we work out temperature change? We need to get the end temperature. So we wait until the reaction stops. So when reaction stops, measure the end temperature. Okay, and then calculate the temperature change, which is just the difference. Okay, once we've done that, we talked about what the independent variable is. So we've done that exact same method. So we just repeat the steps with different metals. And if we wanted to make it more accurate, this is where we're talking your 5, 6 marks. You repeat each one 3 times and calculate a mean. Then the next thing is, to really take it to the very, very top, is you need to talk about what are your control variables. So what are you going to keep the same to make sure that if someone followed this method, they would get 100% the best results that they could get from it. So what things you could control? You could have the same volume of acid. Must be volume, not amount. When we're talking about liquids, it's the volume of a liquid. Same concentration of the acid, because if it's more concentrated, that's going to make it go faster, so we don't want to change that. Same mass of the metal. Can't say amount, got to say mass because it's a solid. And you could also have the form that the metal is in, so that surface area, the metal being in a powder form or solid piece. I would just put same surface area of metal. You're just thinking for that, all I've done there is rattled off what are the things that might affect the rate of this reaction? I mean, you already talked about your concentration and surface area. That's just rates of reaction stuff, isn't it? And then the final mark, is a conclusion. What conclusion can you make from this experiment? Well, how do you know which one is going to be the most reactive down to the least? It's going to be whichever metal has the biggest increase in temperature is going to be the most reactive. So metal with the highest temperature change is the most reactive. There you go. Try and imagine when you're doing these methods, if you were to go into a lab and do this yourself, logically what would the sequence of steps be? Because that's how you're going to scrape towards the 5 and 6 mark questions. Is it in a logical order for someone to follow it as a method, rather than just putting a load of random bits down? Think about the order. Next question. This one is about group 7 elements. What are the group 7 elements known as? Now, for this one, it's kind of a memory thing. The only ones you really need to know is group 1, group 7, and group 0, which is normally it's in your planner periodic table, so hopefully you've seen it enough times at this point to know what the group is called. Group 1 is the alkali metals, group 0 is the noble gases, and then group 7 is halogens. They're just ones that you've got to know off the top of your head. You either know the name or you don't, but hopefully you've seen it enough time, so you do. Next one. Why do group 7 elements react in similar ways? So it says the word react, chemical reaction happening. 99, well, pretty much all of the time we're talking about, when chemical reactions happening, we're talking about something going on with electrons, right? What thing do all of those, in terms of electrons, what do all of the group 7 elements have in common in terms of the electrons? We'll think about what does group 7, what do the groups tell you? The groups tell you how many electrons are on the outside shell. So that's your answer. They have the same number of electrons on the outer shell. Must say outer shell, right? Which shell are you talking about? You're talking about the very last one. So specify that. Must say outer shell. Next question. Figure 3 shows the structure of a molecule of chlorine oxide. First thing, what is a molecule? A molecule is a group of atoms. And then we've got figure 3, says these are chlorine atoms, these are oxygen atoms. What is the molecular formula of a chlorine oxide molecule? First word I'm spotting is formula. What's a formula? Formula is all of the things, chemical formula, molecular formula, all of the different chemicals that you've mentioned throughout high school. The formula would be things like H2O, O2, CO2, etc., CH4. So the symbols with the numbers that tell you how many of each atom is in this formula of whatever this molecule is. So what's the one for chlorine oxide? All you need to do is you look at the picture and it points to the light circles are the chlorine atoms and the dark circles are the oxygen atoms. So you just count them. You always start with whichever elements are most central in the structure of it. So all you need to do is, we'll start with the chlorine atoms. You count them. How many white circles are there? 1, 2. Start off with that. Then you write the symbol for chlorine, which is on your periodic table. You don't even need to remember it. You get your periodic table in your exam. It's Cl. And then when it's in a formula, we can't do a big 2 at the start, because that means everything that follows is there's 2 of everything. So it's going to be a subscript 2 like that. And then we do the same for the oxygen atoms. How many? 1, 2, 3, 4, 5, 6, 7. So then we do a symbol for oxygen, capital O, and then how many? Subscript 7, like that. And that's your formula, Cl2O7. Figure 4 shows the melting points of some group 7 elements, and it highlights the name of all the group 7 elements at the bottom. And it says, and up the side, the melting points. There's your scale. The melting point of fluorine is minus 220 degrees Celsius. Complete figure 4, and then it says you should complete the scale on the axis and draw the bar for the melting point of fluorine. When you see graphs like this, this is literally, it's like a cheat code. It's telling you this is where you will get the marks from. So you just tick them off. You can just tick them off as you do it. So first thing we need to do, we can't plot a graph without a scale on the y-axis. Otherwise, you've got no idea what you're plotting. So the first thing is you just look at all of these numbers down the side. It's just going down in 50s each time. And it's using one of the kind of thick lines each one. So we carry it on all the way to the bottom. So 0, minus 50, then it would be minus 100, then minus 150, then minus 200, and then minus 250, all the way to the bottom. You would get 1 mark for doing that, and you can tick it off as you do it. And it says draw the bar for the melting point of fluorine, which is minus 220. Going back to what we talked about with graphs before, always think about what the little jumps are worth first. I would look at small numbers to make it easy. So from 0 to get to minus 50 or to get to 50, there are 5 little jumps. That means each little jump is worth 10, right? So to get to minus 220, we'll start off at minus 200. How many little squares do we need to go down to get to 220? Each one's worth 10, so it's going to be 2 extra squares. It's going to be like there. And then you just draw your bar with a perfectly straight line, like I've just done. There you go. Done. Easy as that. Question 4.5. Explain the trend in melting points of the group 7 elements. So explain. So it's talking about why is this the case, and you're thinking about melting points. Be very careful with this, because sometimes people read it and then they just go explain the trend, and then just see explain the trend group 7, and then they just go, oh, distance between nucleus outer shell, blah 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 blah. You need to read the question carefully, because we're talking about the melting points. First thing I'm thinking is group 7 elements, things like chlorine, bromine, iodine, astatine, etc. They are all non-metals, right? Which therefore means, what kind of bonding is it? It's covalent. So that means there's a phrase anytime we have covalent bonding. What's a phrase? Especially when it's simple covalent molecules like that, they're talking about intermolecular forces, aren't you? So first thing you need to do is before you give the why, you give the what. So you say, what is the general trend as they go down group 1? What's the general trend in melting point? So you could do it the other way as well as you go up, but you've got to make sure you say it the right way around. So as you go down group 7, melting point increases, right? So that's our what. Then we've got to say why. So first thing we can do is we can talk about, well, what else increases as you go down the group. Think about the atoms themselves of fluorine, then chlorine, and bromine, because the atoms get bigger. Right? And if the atoms are bigger, what's that going to do to those weak intermolecular forces? There's going to be more. They're going to be stronger because of the bigger atoms. So your last mark is, therefore there are more intermolecular forces. It's a bit like imagining it like gravity. You know, the bigger the planet or the bigger the star, the more the pull towards it. Same sort of thing. If the pull is stronger, that means it's going to take more energy to pull them apart. That means the melting point is going to be higher. It's going to take more energy to get them apart, to get them to change state.
So, question 4.6. What is the state symbol for bromine at minus 50 degrees Celsius? So we've got 4 state symbols: aqueous, gas, liquid, and solid. We're talking about what state would it be at if it was minus 50. Now it's not going to be aqueous because we're talking about elements. So we're just talking about the melting point of the element on its own, not when it's dissolved in solution. So we can rule that one out. Then we look at the graph. So we're figuring out what would it be at that temperature. This is a bit of a weird one because you're looking at where the bar goes to tells you the melting point. So if we look at bromine, the middle one, and we look at where the bar goes to, it goes to around about minus 8, minus 9 degrees Celsius, something like that. So it means that if that's the melting point, anything warmer than that temperature, that's obviously not hot enough to get to the boiling point, is enough to make it melt, make it turn into a liquid. So anything below -9 or -8, it means it's going to be frozen, it's going to be a solid because it's not hot enough to melt. So is -50 below those numbers? Yes. So it's a solid. The next one, evaporation and boiling occur at the surface of bromine, so if at its boiling point. So if we imagine we've got bromine in a solution, in a beaker, whatever it will be, and it's boiling, right? The particles at the surface are gaining enough energy to transform, to change state, to transfer into a gas. But at the surface, also, some of the particles are going to lose a little bit of energy to the surroundings, and they're going to end up reverting back into a liquid. So what is the state change? What's the opposite of evaporation and boiling that's happening at the surface? The answer is condensation. Next question. This question is about structure and bonding. The first thing I hear before I even read any further is the 3 types of bonding. So that's ionic, that's covalent, that's metallic. As soon as I see those words. Figure 5 represents part of a carbon molecule. I mean, you hear the word carbon, and first off you're thinking, well, it's made out of carbon. Carbon is non-metal, right? All non-metals, so that's covalent. And when you're talking specifically about carbon, you're talking about those giant carbon allotropes. If you remember them, they are the ones where you just need to remember a few. So then you're thinking straight off the bat, what were the carbon allotropes that we've been talking about? So you've got diamond, you've got graphite / graphene, you've got the fullerenes. So you've got the Buckminster fullerene, which is the big spherical one. You've got nanotubes, carbon nanotube. So they're the ones you need to remember when you are talking about carbon allotropes, giant covalent structures. So then we look, that's just off the first bit of the question. Immediately I'm thinking that. Name the type of carbon molecule in figure 5. So what kind is that? There's 2 answers you could put for this. So the one where because it's got hexagon rings. So this is the one where we talked about the repeating pattern of hexagon rings is called a fullerene. But if you want to be a bit more specific, you still get the mark. Which one is that? It's obvious. It's the tube, isn't it? So it's the carbon nanotube. You can't say Buckminster fullerene for this one because that's the one where it's the sphere of 60 or 70 carbons, which is not what this is. So you can't say that one. So it's just those 2 answers. And the next one, suggest one property that makes the carbon molecule in figure 5 useful for nanotechnology. Properties. What are you thinking? You're thinking melting boiling point, maybe. You're thinking does it conduct electricity or heat? You're thinking is it strong or weak, right? For this one, the most useful part of this one, because it's only making, each carbon's only making 3 bonds, so 3 bonds, that means we have delocalized electrons. So therefore, this one is very good for conducting electricity. It also is good for conducting heat. Either one will work. You could also say because it's a long tube and because of those strong covalent bonds, it has a high tensile strength. So it's very, very strong because they use this to reinforce the material in aircraft, in different kinds of aircraft to make it strong. So it's very good that it's a small material, but it's super strong. That's what you could put for that one. Next question. An alloy of aluminium contains small amounts of other metals. Explain why other metals are added to aluminium. So the first thing I am thinking when I see alloy is the diagram that you'll have been shown when you were taught alloys. So if you have a pure metal, so we take a pure metal, all of the atoms are in a lovely little row, regular pattern like that, and means that the layers they're in perfect regular layers. If we take an alloy, it's a bit more of a mess. So we chuck in random small atoms of different elements. Might be bigger, but just different sizes. So therefore, that pattern is no longer there. The reason for that is when we take the atoms you can imagine a tray of balls of the same size. They would all be able to move around in the tray very easily. If you put a couple of different size balls in the tray, then it doesn't do it the same. They can't move the same. So for this one, the first thing we point out is that there are different sized atoms in an alloy. Okay, what does that do? If we look at this, so this one has perfectly aligned layers and this one does not. So this one, the reason we have different size atoms in an alloy is it disrupts the pattern in the layers. So therefore, what can the layers not do? Well, it's easy. That's the reason why metals are so ductile, is the layers, the atoms can slide over each other and we can mold it into different shapes. If it's an alloy and we've got different size atoms, then the layers can't slide easily. So then therefore, what would the property be if the layers can't slide? The alloy would be harder than pure aluminium. There you go. Next question. Figure 6 represents part of the structure of a polymer. See the word polymer, you think repeating pattern of a monomer, which is normally a covalent substance, right? Non-metals. There's the picture, polymer chain. Compare the bonding within the chains. So bonding within the chains with the forces between the chains. Now the first thing to highlight is the word bonding and the word forces. First thing is, you see the word forces, it's talking about, there's only two options for this when we're talking about chemistry, isn't there? There's electrostatic forces of attraction. What kind of bonding is that? That's talking about either ionic bonding or metallic bonding if it's attracted to the delocalized electrons, or it's talking about those weak intermolecular forces. What are they for? They are for covalent bonding. So that's the first thing we've got, weak intermolecular forces. And then we've got compare the bonding. What kind of bonding is it? If it's a polymer, it's covalent. So let's talk about within the chains first. So within the chains, what kind of bonding is it? There is covalent bonding. That's your first mark. Then we look at between the chains. It's giving you a hint because it says forces. Between the chains, there are weak intermolecular forces. That's your second mark. And then the final mark for that is you are comparing the two. So what's the difference between the two? So, well, weak intermolecular forces, the hint is in the word weak, and you should hopefully know that any type of bonding, especially covalent, is very strong. So all you need to say for the last one is covalent bonding is strong, and to get the mark, weak intermolecular forces are not. You have to put both to get that last mark because you're comparing the two, so you've got to make reference to both of them. So this question is about hydrogen chloride and hydrochloric acid. Complete a dot cross diagram and represent the bonding in hydrogen chloride. And there's two things I'm thinking straight away. I'm thinking bonding, like before. Is it ionic? Is it covalent? Right? Is it metallic? You don't need to do dot and cross diagrams, so it's not going to be metallic. So then we look at dot cross diagram. We need to be careful with this one because there's two different types. There's the one with the brackets with charges, etc. That one's ionic, and then there's the one with the linked circles, which is covalent. But it almost tells you the answer because it's already given you the linked circles. So you're going to use dots and crosses to represent electrons and show only the electrons in the outer shell, just to save ourselves time. If you're not confident with this, what I would do is I would just draw the electron structure of hydrogen and chlorine to start with, right? So hydrogen has one electron, and then chlorine has 7 because chlorine is in group 7. Then we decide what are they going to do. If it's covalent bonding, right? If you remember, what do they do in covalent? They share electrons. So how many does hydrogen need to gain? Hydrogen needs to gain 1 electron to get a full shell, because you can only have 2 on that first shell, and chlorine needs to gain another 1 because it needs to get to 8. So if they both need to gain 1 electron, then they're going to share 1 pair of electrons. So they share 1 pair in the middle like that. And then you just fill in the rest based on what they had to start with. How many did hydrogen have? 1. So that one's done. How many did chlorine have? 7. And there's 1 being occupied in the middle. So we're going to do 6 more to add to the 7 that chlorine had. That's it. Next question. Hydrogen chloride dissolves in water to produce hydrochloric acid. Hydrochloric acid is a strong acid. First thing I'm thinking of when I see the word acid is what makes it an acid, if you remember. So acid is going to be H plus ions, and then your alkalis were OH minus ions. And then it says, what is meant by the term strong acid? So it's all about how easy or difficult it is for those ions to form in solution, those H plus ions. If it's a strong acid, that means it's very easy. So when we put it in solution, it's going to completely ionize in aqueous solution. If it's a weak acid, that means it's, you know, some are going to be changing back into the substance that's going into the solution. If it's strong acid, it means all of the H plus ions are just going to be completely ionized, or completely dissociates is also allowed. Next question. Describe how magnesium can be used to distinguish between a strong acid and a weak acid of the same concentration. So we're talking about magnesium, we're talking about metal reacting with an acid. What happens when you put metals that react with an acid? If you remember, they produce hydrogen gas and they will fizz depending on how reactive the metal is. So the first thing I would put is, I mean, if you were to imagine a miniature method of doing this, you don't even get a mark for this, but you would react with both acids, right? And then obviously it would fizz. Fizz would happen, or fizzing would happen, and if to figure out which one the more reactive acid is, it would happen more for the stronger acid. You could have also put something to do with, rather than fizzing, you could have talked about what else would happen when you react magnesium with an acid. If you remember, it's an exothermic reaction. It means it gives out heat, means you feel it as hot. If the acid is stronger, it's going to react faster, you're going to get a bigger temperature increase. So you could actually get 2 marks for saying the temperature change would be higher in the strong acid. That's also 2 marks. Just being comparative with the two, put it in both, see which one reacts more viciously. Pretty simple. The concentration of hydrochloric acid is increased by a factor of 100. What is the change in pH? So the first thing I'm thinking is talking about acids, and it says pH. What is the pH of an acid? pH of an acid can be 1 to 6. That red to yellow range, because obviously 7 is neutral. What happens to the pH if we increase the concentration by a factor of 100, which is just a fancy way of saying making it 100 times more concentrated? So the first thing to think about is, if an acid is more concentrated, which way on the pH scale is it going to go? It's going to go more towards the acid end, which is the most concentrated acid pH you can get is 1. So if we make it more concentrated, the first thing we can definitely say is the pH is going to decrease. Thinking about words while I was talking at the same time. So the pH will decrease. And then the second thing is how much by. So something that you will just need to know is, every time we make the acid a factor of 10 times more concentrated, the pH will go down by 1. So if it becomes 100 times more concentrated, pH will go down by 2. Question says ethene and hydrogen chloride react to produce chloroethane, and it gives you a formula equation for the reaction, which is here. So it shows you the formula. You're not expected to know that. And it says the reaction is exothermic. So the first thing I think when I see that word is energy is given out to the surroundings, and because we're talking about bond energy, which we'll get to in a second, the overall energy change is going to be negative. So in the reaction, the energy released from forming new bonds is 56 kilojoules per mole greater than the energy needed to break the existing bonds. So there's a few ways you can do this. It talks about giving you some bond energies, and you are calculating the bond energy X, which is the C-double-C bond, which is this one. So we don't know what the bond energy for that one is, and we're trying to work that out. There are a few ways to do this, but I will talk you through how I would do it. So the first thing, so we're trying to work out what X is. We know it's exothermic, so we know, I know from that this number, the overall, I would always do reactants take away products. So the bond energy of the reactants take away the bond energy of the products, and it's going to give us a negative number because it's 56 kilojoules per mole greater. So it's going to be minus 56 kilojoules per mole. Right? So something takes something is going to give us minus 56. Then we need to work out the reactants and products that we do have. We don't have the C double bond C. So what I would do is split the thing into two parts. So we have our reactants. So we're going to find the bond energy of those and the products on this side. So let's do the ones we do know. So the HC bond, we look at the reactants. How many of those have we got? We've got 1, 2, 3, 4. So we're going to do 4 times 413 kilojoules per mole to break those. And then we look at the other one, we've got HCl bond, which, how many have we got? Just 1. So 1 times 431 for those. And then for the CC bond, that's the one we're trying to work out. We don't know what that is. So on this reactant side, I'll do it in a different colour to make it obvious. So you do the total of what you've got so far. So 2083, you put those in your calculator, and something. And we're trying to work out what that something is. Let's do the products. So we've got HC bonds on that side as well. How many have we got? We've got 1, 2, 3, 4, 5 of those. So 5 times 413. And then we'll do the C single bond C ones. How many of those have we got? We've got just the 1. So it's going to be 1 times 346. And then we've got the C bonded to Cl. How many have we got? Just the 1. So 1 times 339. And then you do total all of those. So you'll get 2,750. And then we know so far that the total, if we do these, take away this, is going to give us minus 56 kilojoules per mole. So 2083, add something, take away 2750 gives us minus 56. Right? We'll just leave the units off for simplifying it. Now you could rearrange the whole thing in your calculator if you want to all in one. I'll do it bit by bit to help you. So let's just get the 2750 to that side first. So let's leave those as they are. 2083 plus something gives us minus 56 plus 2750, which is, I have the maths somewhere. Let me hold on. 2,694, right? And then we do, so that's 2,083 plus something, gives us that number. And then we do the last bit to rearrange to get the question mark. So that means that whatever that unknown number is going to be 2,694. What's the opposite of plus 2,083? Take away 2,083 gives us 611. That's your answer. So you're just working out the bond energy of this side, bond energy of that side, reactants take products gave us this number, and then we're just rearranging some simple algebra to find the unknown number. So this question is about elements and compounds. recap, what is an element? So an element is, remember, one type of atom, and your compounds are two or more different atoms chemically combined. So thinking about those when we're answering this question. Figure 8 shows a reactivity series, so from the least reactive up to the most, there's a bunch of elements, and then metal Y, which is an unknown metal. Give a method and conditions used to extract metal Y from a compound of metal Y. So how do we get the pure metal out of a compound that has that metal in it? So there's a couple of ways that you could do this. The first thing I'm thinking when I see reactivity series, what is the number one thing that you were taught and what you were talking about in lesson when you were talking about reactivity series? It was primarily about displacement reactions. So when a more reactive element, metal, will displace a less reactive metal. So first thing you could do, if you look on the reactivity series, you've got potassium and magnesium are both above it. So one way we could do this very easily is we can do a displacement reaction with either potassium or magnesium. So that's 2 marks, one for saying displacement, one for saying with a more reactive metal or naming the metal. Another way to do it, if we didn't have those, the other way, if we don't have anything that's more reactive, is we can also, if you remember, use electrolysis. So electrolysis using electricity to separate it into ions. So the other answer you could have put to get the 2 marks is you can use a electrolysis. That's your first mark. And then what state does it have to be in to be able to do electrolysis? It has to be as a liquid, so molten. So of a molten metal compound. So there's 2 possible answers for that. You only need one. Easiest one is displacement, most obvious one. Sodium reacts with titanium chloride to produce titanium. Complete the equation. You should balance the equation. So first off, we're going to need to complete the equation before we start balancing it. Now we get a hint as to one of the things that is made, because it says here it produces titanium. So we know one of the things that's going to be made in this is going to be titanium. The other thing you should find is you should also know, similar to the previous question, that this is a displacement. Can't write the word displacement today. Displacement reactions, and that's where we've got a more reactive element displacing a less reactive element from a compound. So sodium is more reactive than titanium, so it's going to replace it. So you're going to end up with sodium chloride. Sodium chloride's formula is NaCl because it's both group 1 and group 7. And then we need to balance it. So let's have a look at how many of each thing we've got on one side. So we've got 1 titanium here, 1 there. That's fine, but we've got 4 chlorines here, so by definition we're going to have 4 sodium chlorides coming out the other end for now. And then we look at to see if it'll work the other side. So we've got 4 sodiums in that molecule of sodium chloride now, not molecule because it's a lattice structure, but 4 sodium chlorides, 4 moles of sodium chloride. So that means we're going to have 4 sodiums, and then we can check the whole thing. So how many sodiums? 1, 2, 3, 4. How many titaniums? 1. How many chlorines? 1, 2, 3, 4. Just check the other side. How many sodiums? 1, 2, 3, 4. How many chlorines? 4. How many titaniums? 1. Done. The next question. The reaction between sodium and titanium chloride is a redox reaction. So that means we've got oxidation and reduction going at the same time. And if you remember the old phrase, oil rig, so oxidation is loss and reduction is gain of electrons. Okay, so then it says write a half equation to show that sodium is oxidized in this reaction. So that means it's saying it's lost an electron. So let's have a look. So we started off, if we focus on just the sodium, because we're only worried about the sodium, we've got sodium overall. If it's a sodium atom, what's the overall charge? It's going to be 0 charge. Okay. And then if we look at the sodium chloride, first thing you might need to recap is bonding and structure. Remember, this is an ionic compound, so that means sodium is going to lose one electron because it's a metal, and then chlorine is going to gain it because it's a non-metal. So you've got sodium plus and chlorine negatively charged. So then we just put that into equation. So half equation will be sodium arrow, because it becomes a sodium plus ion, and then it has lost a negative electron, like that. And that's your half equation. 7.4. So 108 grams of aluminium reacts with 1.21 kilograms of copper chloride to produce copper. There's the equation. Calculate the maximum mass of copper that could be produced in grams. Should determine the limiting reactant. So first off, the limiting reactant is the thing that is going to limit the amount of mass that's produced in the end. So the one that's in the least supply. So the opposite of excess. It gives you the relative atomic masses and formula masses. 99% of the time when you are given that, it's going to be talking about, it's going to expect you to calculate moles. So there's going to be some form of a moles calculation in there. And most definitely, because we are given masses, it's definitely going to be a moles calculation. Because if you remember the equation, mass equals Mr. Moles, or you may remember it as moles equals mass over mR. Okay, so first off, for this one, if we're doing moles calculations, then we have to make sure we've converted the masses into grams. That was what I would do first. So that 1.21 kilograms, to convert it into grams, times by 1,000, you get 1,210 grams of copper chloride. What I would do at this point, so we are talking about the limiting reactant and we are figuring out the maximum mass of copper. We're given the mass of aluminium, we're given the mass of copper chloride, we're talking about copper, so this one right here is irrelevant. So also the relative formula mass of that one is also irrelevant. Just putting it in there to throw you off the track. So what I would do is I would use your line section, I would split it into 3 bits because we're only bothered about 3 of the elements or compounds. So we've got aluminium, we've got copper chloride, and we've got copper. Okay, then I would fill in as much as you possibly can. So we're talking about the mass, we got the mR, and we calculate the moles, right? So I would just fill in everything that we can to start with. So we know the mass of aluminium is 108 grams. And we know the mR is 27. So we can calculate the moles because we just do, I'll write it over here. So we just, for aluminium, we just do 108 divided by 27 gives us 4 moles of aluminium in this equation, in this reaction. Let's do the copper chloride. So the mass of it is 1,210 grams. The mR we are given, we don't even have to work it out, 134.5. So then for copper chloride, the moles is 1,210 divided by 134.5, which gives us 8.996 moles. Okay, let's fill in what we've got. We don't know what the mass of copper is. We do know what the relative atomic mass is because it's there. So far you've already got 2 of the marks for calculating the moles for each one. The next thing we need to do is we need to figure out which one of these reactants is the limiting reactant. So obviously we've got a ratio of, if we look, we've got a 2 to 2 to 3. So I'll just write this here. So the ratio is 2 aluminiums. For every 2 moles of aluminium, you add 2 moles of copper chloride to make 3 moles. Sorry, 2 aluminiums to 3 copper chlorides to 3 makes 3 coppers. So then we need to look at which one of these is going to be the one that's limiting the amount of substance that we can make. So if we take this, so let's just look at aluminium to start off with. So if we have 4 moles of aluminium, let's figure out how much copper would that allow us to make. So if we had 4 moles of aluminium, how much would that make? Well, we would just divide it by 2 and then times it by 3. So to work that out, divide by 2 to get it to 1 and then times by 3. Or you could just times it by 3 over 2, same thing. So 4 moles of aluminium would make
6 moles of copper. So we can write that down, right? So 4 moles of aluminium makes 6 moles of copper with what we've got so far. Then we do the same thing for copper chloride. So how much copper would this amount of this mass of copper chloride make? Well, if you look at the reaction equation, we've got for every 3 moles of copper chloride, you get 3 moles of copper. So it's a 1-to-1 ratio. So however many moles of copper chloride we have, we'll be able to make that many moles of copper. So we can write that down. So 8.996 moles of copper chloride would make the same amount of copper. Okay, so which one is limiting the amount of copper that we can make right now? It's aluminium, because aluminium is allowing us to make less. So that's the next mark. Aluminium is the limiting reactant. Right, we can write that down here. Then finally, using that amount of moles that we've got, we need to work out, so therefore if we've got 4 moles of aluminium, then what's the maximum mass of copper that we can actually make? So we use that number. So first off, let's work out how many moles of copper have we got. We worked that out before. So if we have 6 moles of copper, what is the mass? So if you remember the equation from before, it's at the top. I'll write it again down here. So mass equals the moles. So we just sub in the numbers. So the mass of copper is going to be MR of copper, which is 63.5 times the number of moles that we've got, which is 6, which gives us 381. 381 grams is your answer. There you go. Last few questions. So sodium metal and sodium chloride are both able to conduct electricity. So the first one is talking about how sodium metal conducts electricity. In these two questions, the first thing I've thought about is sodium metal, what kind of bonding? Metallic. Sodium chloride, NaCl, what kind of bonding? It's ionic, right? So if it's talking about sodium chloride, you need to be thinking about ions. If it's talking about sodium metal, you need to be thinking about those metal layers and delocalized electrons, right, with the metal ions. So first question, describe how sodium metal conducts electricity. That's the one where we're talking about you've got your positive metal ions in a regular pattern, and then you've got delocalized electrons free to move. So that's where you get your marks for that one. Delocalized electrons, therefore free to move. Okay, now you've got to mention where they are free to move, so just describe either through the lattice. You can't say the word throughout because they can't move everywhere, they've got to move in a specific direction, so just put free to move through the metal. That's your 2 marks. And the next one, last question, explain how sodium chloride can conduct electricity. So this one, remember, is ionic bonding, so we're talking about ions. So when can sodium chloride conduct electricity? It won't do it when it's solid, we know that. It will not do it when it's solid. When will it do it? It will do it when, so it will conduct when it is either molten or in solution, right? You only need one of those to get that mark. Because, why? What can the ions do when they are either in solution, so dissolved, or molten? They can move. So you get 1 mark for saying the word ions, and then they can move and carry a charge. That's your 3 marks, right? 3rd mark for this bit here. You only need molten or in solution, and you say the ions can free to move, carry a charge. You could also put allows the charge to flow because they can move. So just recapping that one, anytime you've got questions talking about anything to do with elements, always think about type of bonding.
You'll never go far wrong if you think about this and then start talking about something to do with whatever the type of bonding is, because everybody can figure out metal, it's metallic, non-metal, ionic, and then two non-metals is covalent. So always keep coming back to this. There you go.